And today we are here to start the lecture series of Mathematics 2. Chapter name is Vector Calculus, and today our second lecture we are discuss about some basic definitions in the last sessions, and today we will discuss about some different definitions of the vector calculus. Curl. In last session we have discussed about the gradient and divergence. In this session, we discuss about the curl. What is curl? A curl of the vector field f bar is denoted by curl of f nabla into f is defined as curl of f nabla into f I del by del x plus j del by del y plus k del by del z into f1 I caret, f2 j caret, f3 k caret. Now to solve this formation, we use determinant ijk del by del x del by del y del by del z f1 f2 and f3. Solve this determinant, we get I del f3 by del y minus del f2 by del z minus j del f3 by del x del f1 by del z plus k del f2 by del x minus del f1 by del y, which is vector quantity. Physical interpretation of the curl. The curl provides the maximum value of the circulation of the field per unit area and indicates the direction which along the maximum value of the occurs. See in this diagram, this is the one. If we are taking here is as a hand formation, if we are taking or finger or clockwise formations, we see that there is this is the directions are create a curl directions. Let us know the curl of the vector field. Green's arrow. This Green's arrow at the each pedal, for this each pedal, show the curl at those point. See, they are going to these directions. If it is rotated, then they are going to these directions. If it is rotated, then they are going these directions. Notice that we can tell how quickly a pedal will rotate by the magnitude of the curl, and we can tell whether each wheel rotates clockwise or counterclockwise by the direction of the curl. The direction flows right-handed rule. If right-handed rule, that means that means the direction of this right-handed rule, and they are going to this type of the directions. If you curl your right hand so that your index finger through pinky follow the flow of the water around the point. See, they all follow the order of the curl. Then the thumb will point in the direction of the curl vector, and this point is the curl vector. Okay. Irrotational field. Irrotational field, that means a vector field f is said to be irrotational if curl f 0 at the point of the function, otherwise it is said to be a rotational. Irrotational, that means it is rotate or not. If it is not rotate, then curl of f is 0, that means there is a one pointer is 0. If it is rotational, then it is not the 0. Conservative field and the scalar potential function. The vector field f bar is conservative if there is a scalar potential function phi such that f bar equal to nabla phi. U xyz, v xyz two vector point of function for the scalar point. This is the curl. This is a property of the curl to satisfy the associative property, addition property, and multiplication property. And this is the curl directions. See. Example. Show that f bar equal to y square minus z square 3yz minus 2xi caret plus 3xz plus 2xyj caret plus 3xy minus 2xz plus 2zk caret is both solenoidal and irrotational. These are summer 13 and winter 14 example. Nebula f bar, del f1 by del x plus del f2 by del y, del f3 by del z. What is del f1? F1 is this. F2, our f1 is y square minus z square plus 3yz minus 2x. What is del f1 by del x? It is minus 2. What is f2? f2 is 3xz plus 2xy. This. Okay. So, del f2 by del y, we have 2x. Similarly, del f3 by del z. What is f3? f3 is 3xy minus 2xz plus 2z. Differentiation of this minus 2x plus 2. Now del f bar equal to 0 for the irrotational. We take curl formula I, j and k, del by del x, del by del y, del by del z. f1, f2 and f3. Take the determinant. Answer is 0. So f is solenoidal and irrotational. Show the vector field f bar equal to y square z cube I caret 2xy z j caret 3x y square z square k caret is conservative vector field, and find the function of f such that f bar is nebula f. So for the conservative field, we have to prove that the curl of f equal to 0. Taking formula of the curl I caret j caret k caret del x, del by del x, del by del y, del by del z, it is f1, f2 and f3. Taking this determinant, answer is 0. So we say that curl of f equal to 0, the domain f bar in R cube. So f bar is conservative field. Now we have to find the function f bar equal to nebula f, y square z cube I caret plus 2xy z cube j caret plus 3xy square z square k caret. I del f by del x, j del f by del y, k del f by del z. Comparing both the side, equation 1 and 2, we get del f by del x equal to y square z cube, 2xy z cube equal to del f by del y, and 3xy square z square equal to del f by del z. Now integrating equation 1 with respect to x, integrating equation 2 with respect to y, and integrating equation 3 with respect to z. We get xy square z cube g1yz, g2xz and g3xy. All are constant integration coefficient. Now what is f? F is xy square z cube, xy square z cube, xy square z cube. So this is our actual function of this vector field. The Laplacian operator nebula square. A Laplacian operator, that means nebula square, nebula into nebula, is defined as nebula square, nebula into nebula, that means del square upon del x square plus del square upon del y square plus del square upon del z square. If f is scalar point function, then del square f is del square f by del x square, del square f by del y square, del square f by del z square, which is scalar quantity. F is vector point function, then del square f bar, del square f by del x square, del square f by del y square, del square f by del z square, which is also vector quantity. This is your scalar quantity, this is your vector quantity. The equation nebula square f equal to 0, then it is called Laplace equation. Important vector identity for the Laplace and all the curl. U and V are vector point, phi is scalar point of function, then gradient of u into v. U equal to nebula into v plus v, nebula into u plus v into nebula, u plus u into nebula v. Divergent of gradient of phi. Divergent of gradient of phi. So, nebula into nebula phi equal to nebula square phi. Curl of gradient of phi, nebula into cross nebula phi. So it is 0. Divergence of curl u, nebula into nebula u equal to 0, and gradient of division u, divergence of u, nebula into nebula u. So these are most important identities. Taking example, given r under root x square plus y square z square. So we show that the scalar function phi 1 upon r is follow the Laplace equation. What is the Laplace equation? Laplace equation say that it is a nebula square of phi equal to 0. So what we prove? We prove that nebula square phi equal to 0. What is a nebula square phi? Del square phi by del x square, del square phi by del y square, del square phi by del z square. But what is our phi? Phi is 1 by r. So we are taking phi as 1 by r. Del square 1 by r upon del x square. Del square r minus 1 del x square. Del by del x r raised to minus 1. What is our r here? R is r square, x square, y square, z square. So we take x square, y square, z square raised to minus 1 by 2. Now we are differentiate one time with respect to x. We get minus 1 by 2 x square, y square, z square raised to minus 3 by 2 into 2x. We are differentiate again del by del x by u by v formations. We get x square, y square, z square raised to 3 by 2 minus x as it is into 3 by 2 x square, y square, z square raised to 1 by 2 into 2x. This is a denominator, differentiation of x is 1, x as it is, differentiation of denominator, and in denominator there is whole square. Solve this formation, we get minus 1 upon r cube plus 3x square upon r raised to 5 formation for the del square phi by del x square. Similarly, we get del square phi by del y square equal to minus 1 upon r cube plus 3x square upon r raised to 5. Okay, here is y. Del square phi by del z square equal to minus 1 upon r cube del z square upon r raised to 5. From the equation 1, we put all the values in this minus 1 upon r square. This value is noted as del square phi by del x square. This is del square phi by del y square. And this is del square phi by del z square. Okay. Solve this. Minus 1 upon r cube, minus 1 upon r cube, minus 1 upon r cube. So minus 3 upon r cube. R raised to 5 are common. So we take addition of in numerator 3x square, y square, z square. But what is x square, y square, z square? It r square. So we take minus 3 upon r cube plus 3r square upon r cube. Minus 3r cube plus 3r cube, it is 0. Hence, it is proved. These are follow the Laplace equation. Example 2. Nebula square f of r equal to f double dash r plus 2 by r f dash r. This is a summer 2012 example. We know that phi is a scalar function and nebula square phi equal to nebula into nebula phi. So what is nebula square f of r? It is nebula into nebula f of r. Divergence of gradient of f of r. Divergence of f dash r gradient r. What is f dash r? F dash r, say it is 1 upon r. What is gradient of r? Gradient of r is 1 f dash r into r bar. So find the divergence. 1 upon r, f dash r, divergence of r bar as it is, gradient of 1 upon r, f dash r. Taking 3 by r, f dash r, because of divergence of r equal to 2 plus r bar d by dr 1 upon r, f dash r, gradient of r. Take 3 by r, f dash r plus r bar into minus 1 upon r square, f dash r plus 1 upon r square, f double dash r into 1 upon r, r bar. 3 by r, f dash r for the 1 upon r minus 1 upon r square into f dash r, 1 upon r, f double dash r. For this case, 1 upon r bar, there is r bar, r bar. 3 by r, f dash r, 1 by r as it is, minus 1 upon r square as it is, f dash r as it is, 1 upon r as it is, f double dash r. R bar into r bar is r square. 3 by r, f dash r minus 1 upon r, f dash r, because r square is cut, so it is minus 1 upon r, f dash r. r square r is cut, r is cut, so we have only f double dash r, and solve these, we get f double dash r plus 2 by r f dash r. So this is a proof any identities using some important property of the curl, divergence, gradients, and scale and Laplacian coordinates. Okay, thank you.